good morning, good afternoon. It is my great pleasure to introduce today's ISQGD distinguished speaker, Professor Christian Wolf. He is a professor of mathematics and department head in the Department of Mathematics and Statistics at Mississippi State University, USA. Professor Wolf's research lies at the intersection of ergodic theory, dynamical systems, thermodynamic formalism, and computability theory, with additional applications to areas such as mathematical biology. He earned his PhD in mathematics from the Technical University of Munich, Germany, and has developed a strong international research profile through influential contributions to geometric, ergodic, and dimension theoretic aspects of smooth and symbolic dynamics. His work explores dynamics on manifolds, symbolic shift spaces, and complex dynamical systems, including topics such as zero temperature limits, rotation sets, entropy, and measures of maximal dimension. Professor Wolf has published widely in leading mathematical journals, reflecting a broad vision of modern dynamical systems and their applications. Through his leadership and research excellence, he has made significant contributions to the international dynamical systems community. Please join us in warmly welcoming Professor Christian Wolf to the ISQ Distinguished Lecture Series.
Thank you very much, Mrinal. Apologies to everybody in the audience for being so late. Apparently, there was a technical issue. Anyway, let's start with the talk. So this talk is on the edge between computability theory and dynamical systems. In particular, I will talk about symbolic dynamics, coded systems, and measures of maximal entropy. First, give you an overview about the general theory, and then give you an idea whether we really can compute these measures if they are unique and if they have a particular property. So the talk will be based primarily on two papers, one with my colleagues Tamara Kucherenko and Martin Schmoll from 24, where we explored the uniqueness and the structure of MMEs for coded shifts. And the second paper is a recent preprint with also with Tamara Kucherenko and with Marco Lopez, which is on the archive, where we explored the computability of MMEs on coded shift spaces. So let's start with the overview. I'm not assuming too much knowledge from dynamical systems, so I will try to keep the talk self-contained and introduce the primary objects of this talk. So I will start with a very, very light introduction to ergodic theory, a brief introduction to symbolic systems, and I will talk a little bit about coded systems, which are generalizations of sofic shifts, and will present a couple of results about the topological entropy and measure of maximal entropy for coded shifts. After that, we move on to the computability part with a crash course, 2 minutes or maybe 3 minutes to computability theory, and I will present our recent results about the computability of MMEs. Now, regarding computability, by this we mean Turing computability. In particular, it's not a numerical analysis approach. The approach is an object is computable if it can be determined by a Turing machine, meaning a computer program, a computer algorithm, at any pre-described accuracy. In other words, the algorithm has as an input the accuracy of the approximation, and the output is the approximation, and that will precisely have that closeness to the real object. So that's the overview. So very, very brief. We will consider topological dynamical systems in this talk given by a compact metric space X. The metric will be denoted in general by D, and F is just a continuous self-map on X, which we iterate. We get the orbits, we get the long-term behavior of a point X, which starts at a given point. The first question one can intuitively ask if one has a topologically dynamical system is, what kind of different orbit behaviors do exist? And to make this question a little bit more precise, an approach is to see when can we really distinguish an orbit. And in reality, in applications, in computer simulations, you can just distinguish orbits if they are far enough apart that one can distinguish them within the margin of measurement. And this far enough apart, once we iterate two orbits, can mean at any point of the iteration, it's enough to be that at some point one can distinguish the 2 points. To make this mathematically precise, this can be done by the Bowen metric. Take 2 points, x and y, iterate them k times, and the Bowen metric dn of the 2 points is then the maximal distance between the iterates at the same iteration k. Just think about you have 2 points which are very, very close together. You iterate them 100 times. If they are at one point of the iteration further apart than margin of measurement, then we can distinguish them being different orbit segments. And the topological entropy is now the exponential growth rate of the maximal numbers of points one can still distinguish within that Bowen metric. So in other words, we fix n, we fix a small epsilon, and we denote by capital N epsilon n the maximal cardinality with respect to the inclusion of n epsilon separated sets. And they are n epsilon separated if 2 distinct points in the set are in the Bowen metric greater or equal than epsilon. And then one looks at the exponential growth rate of the number n epsilon n. So in other words, if that n epsilon n grows by e to the alpha n, then alpha will be the topological entropy of the system. Okay, so that's topological entropy. Now, there's also measured theoretic entropy, which is essentially the same or similar than topological entropy, just by ignoring sets of measure 0. So more precisely, let's look at the space script M, the set of all F invariant Borel probability measures on X. We can endow this space with the weak star topology, which makes script M a compact convex metrizable space. And the measured theoretic entropy of an invariant measure one denotes by h mu f, and the variational principle tells us that the topological entropy is the supremum over all measured theoretic entropies. And whenever the supremum is attained, we say that's a measure of maximal entropy. So roughly speaking, a measure of maximal entropy is a measure for which the typical points already carry the entire orbit complexity of the system. Now, in general, an MME doesn't have to exist, but for certain systems, in particular symbolic system, it will exist. And if it exists, it's also not clear whether it's unique and what is the structure. So it's a natural question to ask, when is the MME unique? Does it exist? What is the structure? What are the properties? And so forth. And there's a wide array of research done about MMEs. So much about these notions from ergodic theory. Let's go to the background in symbolic dynamics. So we look at finite alphabet symbolic spaces. So let's select an alphabet A of these symbols, typically denote by 0 to d minus 1. And let's look at the space of all bi-infinite sequences of symbols and call that the full shift in these symbols, denoted here by sigma. The shift map, so since we have bi-infinite sequences, there is a center where x0 starts, so it comes also with a location. Every sequence comes with a location where x0 starts, and the shift map is now just the map which takes a sequence and moves it by one increment to the left. That's the shift map. The shift map is a homeomorphism on the full shift. And well, since it's a homomorphism, let me quickly tell you the topology on sigma. The topology is just the Tychonoff product topology, and it's metrizable here. I have one way how to define the metric which gives you the Tychonoff product topology. Essentially, the idea in this metric is just if 2 points in a centered segment coincide, where the length of the segment is 2k plus 1, then the distance is sigma is theta to the minus k, actually. Is that correct? Yes, then the shift map is theta to the k. Typically we use theta equal to 1, but that's not really important. So this is now the full shift. It's a topological dynamical system, but there are many subsystems which we call subshifts. What's a subshift? A subshift is just a subset of the full shift having the property that it's closed, hence compact, and it's shift invariant. And there's an uncountable set of subshifts on this full shift, and the dynamics can be very different depending what subshift one uses. Now, there's another notion for a subshift, which is the language of the subshift. Just take a subshift and look at the set of all finite words which somewhere occur in one of the sequences in the subshift. And it turns out that knowing the language defines the shift space, and having the shift space defines the language. So in other words, languages and shift spaces are identical objects. Okay, some examples. The most studied and well understood examples are so-called subshifts of finite type. A subshift of finite type is a shift space which can be defined by a finite set of forbidden words. So you take a finite set, call that the forbidden words, and you take the largest shift space which omit any of the forbidden words. That's called a subshift of finite type. Now, the largest length of the forbidden words we denote here by L, and in this case, X is called an L-1 step SFT. This means, where does this step comes from? Think about a sequence going through, running through a tape, and you want to know at the tape whether a symbol K can occur. For that, you need to know the L-1 previous symbols in order to make sure that these symbols concatenated with the K is not a forbidden word. That's where it comes from. Now, if L is equal to 2, we have a one-step SFT, which means the set of forbidden words, a maximal length is 2. In that case, we can represent the SFT by a transition matrix, A with elements Aij, and the rule is just Aij is equal to 1 if an I can be followed by a j, and Aij is equal to 0 if I can be not followed by a j. And it turns out when we have any subshift, we can always go to a larger alphabet and make and find an isomorphic subshift, which is of step 1, so which can be represented in particular by a transition matrix. And therefore, the only spaces for subshifts for SFTs one has to look at are really those where which are one-step SFTs, because up to conjugacy they are just identical. Simple example: if you take two symbols 0 and 1, and you allow all words except the word 1, 1. So after 1 must always come a 0. You get the golden mean shift, and one can quickly compute the entropy. In that case, the entropy is just logarithm of the golden mean. A slightly more general class of shift spaces are so-called sofic shifts. By the way, can everybody hear me?
Yes, we can hear you.
Okay, because
Yeah,
I hear
no
nothing.
problem.
Okay, very
Yes,
good.
everything is all right.
We have SFTs given by a transition matrix, respectively by a finite set of forbidden words. Slightly more general are so-called sofic shifts. Sofic shifts can be defined by looking at a finite directed labeled graph where the labels are just numbers in the alphabet associated with each edge. And then one looks at the set of all bi-infinite paths on that graph and takes the corresponding sequences, and that is the sofic shift. So sofic, in particular, subshifts of finite type are sofic, but there are sofic shifts which are not SFTs. For instance, the even shift. The even shift is the shift on the symbol 0, 1, where the numbers of zeros which start with a 1, then a number of zeros, and then a 1 is just even. So you have just words, even words of consecutive zeros, and that's a sofic shift which is not an SFT. But still, they are very, very closely related. Namely, sofic shifts are precisely the factors of SFT. And for sofic shifts and SFTs, Perry's result for SFTs gives us that there's a unique measure of maximal entropy. In fact, there's a nice formula that Perry established. And then for sofic shifts, one can use the Coven-Paul result to get the factor which is finite to 1, and one just carries this result over. So transitive sofic shifts also have a unique SFT, which a unique measure of maximal entropy, which can easily be computed. Okay, so this is the review. Let's make it a little bit more general. Let's talk about coded shifts. So what are coded shifts? Coded shifts are similar like sofic shifts, but now allowing an infinite set of words defining the shift space. So here we take a set of generators denoted by G. The generators are called GI. And one looks at the set of all possible bi-infinite concatenations of generators. And the coded shift X, denoted by the generating set G, is now the smallest shift space which contains all bi-infinite concatenations of generators. So in particular, a coded shift can be defined by various different classes of generating sets. The only thing is just, the only condition is that the smallest shift space containing all bi-infinite concatenations is the same shift space. So in other words, the set of generators which defines a coded shift is not a unique thing. But once you have a generating set, you get your coded shift. So the set of concatenations of generators, one typically calls the concatenation set, and the coded shift is then just the topological closure of the concatenation set. In particular, if the generating set is finite, then you don't get any points by taking the closure, and you get a sofic shift. If it's infinite in general, it's not a sofic shift. And we will, in this talk, only consider the infinite case, because sofic shifts, as I mentioned, are well understood. Now, the set of points you add when you take the closure, we call the residual set, again, dependent on the generating set G. And as I mentioned before, both the residual set and the concatenation set depend on the corresponding generating set. So I have here some references about papers, particular Blanchard Hansel, introduced coded shifts, Fiebig, Link Marcus, the symbolic dynamics book has a chapter about it. And then we have a paper in 22 where we looked a little bit more about the computability for coded shifts. All right, so as I mentioned previously, for coded shifts, there could be multiple sets of generating sets, which give you the same coded shift. We say a coded shift is uniquely representable if there's a generating set such that each concatenation sequence has a unique representation as a concatenation of generators. So in other words, if you have a point which is a concatenation of generators, there's no other concatenation of generators which gives us the same point. And it was an open question for quite some time whether every coded shift is uniquely representable. This question was recently solved by Ɓîl, Perrin, and Restivo, who proved that every coded shift is uniquely representable, and the proof is constructive. So in other words, if you have any generating set, you can define a coded shift. Then there's a construction how you change this generating set such that the coded shift is the same, but the generating set uniquely represents the concatenation set. And since we have this result, we can from now on just assume that the generating set uniquely represents the concatenation set. So this result by Ɓîl, Perrin, Restivo can be computerized. In other words, if you have a sequence of generators plugged into a computer program, you can write a computer program that the output is a new sequence of generators, such that these two sequences give you the same coded shift. As well, the second one uniquely represents the concatenation set. I have some examples of coded shifts: transitive SFTs, sofic shifts, coded S-gap shifts. We will talk about them a little bit later. Multiple gap shifts, beta shifts are prototype of examples for coded shifts. All right, so the main idea in looking at MMEs, looking at entropy, looking at topological pressure here is to split up the corresponding invariant we look at, in that case, the entropy, into the concatenation entropy and the residual entropy. The concatenation entropy is just the supremum over all measure theoretic entropies, where the only measures are considered which put full measure on the concatenation set. And then we define the residual entropy in the same way, just restricting measures on the, which put, restricting to invariant measures which put full measure on the residual set. Here one needs to make clear, obviously, that the concatenation respectively residual set, a measurable set, and actually that's not that easy to prove, but it can be proven. It's actually in our paper, which I cited from 24. It's shown that these sets are, in fact, really measurable sets. So these are well-defined quantities. Now, by the variational principle, the topological entropy is just this primum of the concatenation and or the maximum of the two entropies, concatenation entropy and residual entropy. And therefore, we can look we can study the different cases. Either the residual entropy is larger, or the concatenation entropy is larger, or they're both the same. So the first kind of naive question, let's call it question 0, is, can we compute the entropy of a coded shift by knowing the generating set? And the answer is yes, sometimes. Namely, we can always compute it just based on the generators, in case there's a measure of maximal entropy which lives on the concatenation set, meaning which puts full measure on the concatenation set. In this case, it turns out that the topological entropy is the logarithm of lambda star, where lambda star is the unique solution of this characteristic equations, which is just lambda to the minus g summed up over all g is equal to 1. And this can be computed in case that this lambda star can be computed, and so we can compute the coded shift, we can compute the entropy of the coded shift, assuming there's an MME which puts full measure on the concatenation set. Moreover, in this case, it turns out that we can approximate the topological entropy from below by the topological entropy of sofic shifts, which just are constructed by taking the first M generators. So we take the first M generators, we get a sofic shift because it's a finite generating set. We get a topological entropy, and if we take the limit m to infinity, we get the topological entropy of the coded shift in this situation. So in other words, there's a sequence, an increasing sequence of coded shifts, such that in the limit the entropy converges to the entropy of the shift space. This is what one calls an almost sofic space. Now, some coded shifts are almost sofic, but it turns out many are not. Namely, this criteria that there's an MME which puts full measure on the concatenation set is an if and only if statement. So if this measure does not exist, it's not almost sofic. All right, so let's think about these three cases. Let's go first to the case where the concatenation set and the residual set have the same entropy. In this case, uniqueness of the MME is in general not happening. So here I state a theorem, but in reality, it's more an example of a coded shift of an alphabet with 5 letters, with 5 symbols, where there are precisely 3 ergodic measures of maximal entropy. Here's the constructions. Essentially, you take this generators Gn and take the union overall n, where you have a concatenation of a word V, W, and 4 followed n times by each other. V is an arbitrary word in 0, 1 to the power n. W is an arbitrary word in 2, 3 to the power n. Then one can show for this coded shift the topological entropy is log 2. In particular, in the residual set, the subshift of 2 symbols 0, 1, the full shift over these 2 symbols, this is the measure of maximal entropy is a measure of maximal entropy for the coded shift. Same for the symbols 2 and 3. And then there is an additional ergodic MME, which lives entirely on the concatenation set. So in other words, if you have equality of concatenation residual set, in general, uniqueness doesn't hold. This is just one example. Let's go to the, I would say, the good case or the natural case where the concatenation set is larger than the concatenation entropy is larger than the residual entropy. It will turn out in this case the MME is unique, and it has a property which we call 𝔾-Bernoulli. It's a 𝔾-Bernoulli measure. Let me quickly explain what that means. So we have the generating set G. Let's assign to each generary a probability Bg, and let's assume there's a constant C greater than 0, such that if we take the G cylinder generated by G0, G1 up to Gk, the measure of that G cylinder is just the product of the corresponding probabilities Pgi divided by the normalization constant C. Now here the G cylinder is something very different than the standard cylinder. The G cylinder is a subset of the concatenation set, which starts at x0 with G0, then you have G1 up to Gk, and you look at all points in the concatenation set, which at this block have precisely the same generators. So in other words, you fix a window in your sequence. In this window, you have a finite block of generators, and then you look at all possible points in the concatenation set, which at these windows have the same generators. So here we particularly use that the generating set is considered to be uniquely representable. In other words, every point in the concatenation set has a unique representation as a concatenation of generators. Okay? It turns out if you have a measure which puts full measure on the concatenation set, knowing the measure on the G cylinders defines already the measure. So it's the same like regular cylinders, standard cylinders. So here, keep in mind this formula. So the a measure is 𝔾-Bernoulli if it's just the product of corresponding probabilities times a normalization constant. You might ask, why do we need a normalization constant? This is because the cylinders, the generators, in general, have a longer length than 1. So if you start at the center with a generator and you want to cover all points, you still need to shift through up to G0 is completely left of X0. And the generating, the normalization constant C takes care of that. So this is a 𝔾-Bernoulli measure, but it's kind of very similar than Bernoulli measures, just the probabilities are associated with the generators. All right, here's the theorem for the uniqueness of the MME, the main theorem for coded shift spaces. So we have here a coded shift space with a generating set which uniquely represents the concatenation set. We are in this, let's call it good case, concatenation set. Entropy is greater than the residual entropy. Then X is a unique measure of maximal entropy, mu max. The measure is 𝔾-Bernoulli. And the probabilities and the normalization constant have an explicit formula, namely the probability Bg is just exponential of minus length of G multiplied by the topological entropy of X. And the normalization constant is just the sum over all these terms, each of them weighted by the length of the generator. So we have an explicit formula in this case for the measure of maximal entropy. And by explicit I mean that we precisely know what's the measure of the individual G cylinders. The parameter C is called the Vere-Jones parameter of a generating set. Vere-Jones has an important paper classifying infinite graphs, countable infinite graphs in the late 60s, and there in the classification of these graphs, the parameter C shows up. Turns out it's very, very important in this context. So a corollary to this main theorem is that once a concatenation set is smaller, corollary is if there's a subshift of the coded shift X on which the measure of maximal entropy lives, or one of the measures of maximal entropy lives, then the concatenation entropy must be smaller or equal than the residual entropy, because this situation cannot happen if we have the 𝔾-Bernoulli measure of the previous theorem. So because there is no proper subshift which contains the concatenation set, this is just not possible. And this inequality is strict due to the previous example. Now, in this talk, I do not consider the case where the residual entropy is greater than the concatenation entropy. Let me just say that in this case, in general, the MME is not unique, and there are many, many examples with various cases of different MMEs, including infinitely many ergodic MMEs. So this case is really, I would say, the case, where in most cases uniqueness just doesn't occur. Oh no, that was not it. Okay. Let me see. Okay, let's now go to the introduction to computable analysis. So let's shift gears completely, forget about very briefly about symbolic dynamics. So what does it mean that a real number is computable? This notion is based on the concept of an oracle. So what's an oracle? An oracle of a real number X, or of a Euclidean vector in Rm, is just a function psi from the naturals to Qm, or on the real line from the natural to Q, such that the value of the function psi at n is 2 to the minus n close to x. So in other words, an oracle is just a Cauchy sequence which converges to the real number at this exponential rate. And obviously, there are oracles for all possible real numbers, but a real number or a real vector, real valued vector, is computable if there's a Turing machine, a computer program, which produces an oracle of X. Now you might think, well, every real number or every vector in Rm should be computable, but think about it. A Turing machine is produced by a computer program, and there are only countably many computer programs. Therefore, the number of computable real numbers of computable real valued vectors is just countable. So most real numbers are not computable. But nevertheless, there are many real numbers. For instance, rational numbers are computable. The program just is print P over Q. Algebraic numbers are computable because we have good algorithms where we know the speed of convergence of algebraic polynomials. Some transcendental numbers like e or pi are computable because, again, we have algorithms which compute e and pi at any pre-described precision. But as I mentioned before, there are only countably many real numbers. Now, this is the object computable numbers. Now, let's think about what it means to be a function, a computable function. And again, let's keep it very simple. Let's stay on Rm. So let S be a subset of Rm, and the function g is now from S to R. We say it's computable if there's a Turing machine, Xi, such that for each x and for each oracle psi of x and for any n, the output of the computer program is a rational number, which is 2 to the minus n close to the value of the function g at x. So here the input in the computer program is an oracle, which is a sequence. So in other words, the computer program has access to a sequence, but the computer program must produce an output at finite time, which means the computer program must decide when is the oracle psi a good enough approximation to make the computation of g of x at precision 2 to the minus n. So besides the oracle input, the second input is n, and n is just the precision at which the computation has to be performed. So this is what I meant at the beginning of the talk when I said Turing machine which produces the object at any pre-described margin of error. The margin of error is here 2 to the minus n. All right, so the good news is here that the inputs of a computable function do not only have to be computable numbers. So as you see in this definition, S can be an arbitrary subset of Rn, and for every x in the domain S, the input in the computer program will be just an oracle approximation of x. What's here also important in this definition that you must have one Turing machine for the entire function to be computable. So it's not possible, for instance, that you have countably infinitely many Turing machines because you cannot combine them into one single Turing machine. So one Turing machine must be able to compute the value of the function. Now, it looks like a fairly mild definition, but it turns out it's pretty restrictive. So for example, computable functions are continuous. This just can be easily shown from the definition because when you take an oracle approximation to some length, you always can change the oracle later on to a point x prime close to x, and still the approximation must be good enough. That's essentially the idea of the proof that computable functions are necessarily continuous. And to show that a function is not computable, the most standard tool is just showing it's discontinuous. So for example, the characteristic function of 0 is not a computable function. But if you have a function that's not computable, it's often possible to restrict the domain and make it computable. For example, if the characteristic function of 0, you can just take the domain by cutting out the 0, and then it becomes a computable function. Okay, so this is now for functions on Rm. But in general, we want to compute more general objects. For example, as I announced in the talk, we want to compute what it means that a measure is computable. So we need to generalize the notion of computability in Rm, and we can do that by looking at so-called computable metric spaces. What's a computable metric space? It's a separable metric space, XD, together with a countable set S, which we call the set of ideal points. It must be dense, and it must have the property that the distance between points in the set S is uniformly computable. Just think about on the real line, the set of ideal points, the approximation would be the rational numbers. So here, but here we have a very general setup. So every separable metric space can be made into a computable metric space, assuming there's a countable dense set where we can compute the distance by one Turing machine. Okay, so let's give some examples. For example, previous page, Rm together with the Euclidean distance, ideal set being all values in Rm with rational coordinates is a computable metric space. Clearly, the distance between rational vectors can be computed by a computer program. If we have a computable metric space, we can look at the set of all compact subsets and endow this space with the Hausdorff metric. That is also a computable metric space. And you might ask yourself, what are the ideal points in this set? These are just the finite subsets of ideal points in the ideal set of the underlying computable metric space X. For example, there are many results in the literature where Julia sets are evaluated whether they're computable. And here one can use precisely that. So a Julia set is computable if there's a computer program which outputs a finite set of rational of complex numbers with rational coordinates, such that this finite set in the Julia set has 2 to the minus n Hausdorff distance to the Julia set. In other words, if you can print the Julia set accurately in a computer screen. Now, every shift space is a computable metric space. Clearly, it's a separable metric space. You might ask yourself, what are the ideal points? Just take any cylinder and select one point in the cylinder. This gives you a countable dense set. For example, you can take the lexicographic supremum in the cylinder, and that makes a shift space to a computable metric space. So in other words, we can now say what it means that a point in a shift space, a sequence in a shift space, is computable. Also, the space of all shift spaces carries a computable metric space structure. There's a natural distance between two shift spaces. You just order the language in non-decreasing length and say the distance between two shift spaces is 2 to the minus n if the nth word in that order differs between the two shift spaces. And what are the ideal sets for the space of a shift spaces? The ideal sets are just the subshift of finite type. So in other words, a shift space is computable if there's a computer program which approximates it in the metric coming from the associated with the language by subshifts of finite type in a prescribed accuracy. Now, in this talk, we want to talk about computability of measures. So how can we compute measures? Let's look at the computable metric space XDS, and that can be made. That computable metric space structure can be taken to define a computational metric space structure in the space of all F invariant borrow probability measures Nx. And how is this done? So what are the measures which are the ideal set? Here, Mx is not invariant measures, it's just borrow probability measures. What are the ideal sets? The ideal sets are just the set of convex sums of Dirac measures, where the Dirac measures are supported on ideal points in X. So essentially, you take a finite set of Dirac measures, you assign to it probability weights, and the points defining the Dirac measures are just ideal points in the set. So in other words, measure is computable if we can approximate it by a computer program at any pre-described accuracy as a finite set, a convex combination of point measures supported on ideal points in X. Okay? So now with this definition, we can ask ourselves, can we compute the MME? So here's the main theorem in this setup. So we look here at the situation of a coded shift with a generating set which uniquely represents a concatenation set. And we assume, the only assumption we have, that there's a measure which puts full measure on the concatenation set and maximizes the concatenation entropy. So we allow that the concatenation entropy could be smaller than the residual entropy, but we want to have a measure which attains full concatenation entropy. So in this case, this measure is unique. It's 𝔾-Bernoulli with the corresponding probabilities the same like in the uniqueness result before. So PG is just the exponential of minus length of G multiplied by the concatenation entropy. And the normalization constant is just the sum of these probabilities weighted by the length of G. That was the Vere-Jones parameter. And now in this setup, it turns out that if the concatenation entropy and the Vere-Jones parameter C are computable, then the measure mu is computable. And here the computability means that the computer program which computes the maximizing measure on the concatenation set must have oracle access to the generating set and the language of the coded shift. So essentially, there's a tape producing the generators, there's a tape producing the language. The computer program asks for large enough number of generators, large enough words, all in non-decreasing length. And then it makes a computation, outputs an ideal measure, which is a 2 to the minus n approximation of the maximizing measure on the concatenation set. So here, the key in this theorem is really that the Vere-Jones parameter must be computable. And that's actually a quite difficult task, because the computability of the Vere-Jones parameter must be based on oracle access of the generators in the language. At finite time, the computer program only knows finitely many generators, finitely many words in the language. So couldn't it be that the later generators, the longer words which have not been designed can be different by producing a different Vere-Jones parameter? And in fact, it turns out that is possible. So we need some additional information to produce that, to translate this theorem into computability result for the MME. And that's done in the next theorem. So here, we are now assuming the case where the concatenation entropy is larger than the residual entropy. And we assume that the topological entropy is greater than this number B of G, which is defined here above the theorem, which is essentially the supremum of all entropies of all individual defined of coded shifts given by generators of the same length. And in the theorem, not only we have to have that the topological entropy is larger than this parameter B of G, we also need to know that the gap between these two values is computable or is given by an oracle. So if this is possible, if the gap is given, then one can compute the Vere-Jones parameter and the unique MME is computable. Now, you might think, well, the B of G is always smaller than the entropy. We don't know that. In fact, but we also don't know any counterexample. But even if the B of G is smaller than the entropy, we really need the gap as an input. So we need some additional information about the coded shift in order to produce the computability of the unique MME. Now, this looks like a very, very restrictive theorem, but it turns out for most of the well-known examples of coded shifts, this theorem immediately produces computability. For example, the case of the beta shift. So the beta shift is a coded shift which comes from the beta transformation. Take a real non-integral number greater than 1, and look at the map on the unit interval x goes to beta mode 1. That's the beta shift. And there is that's the beta transformation. And when you take the corresponding partition coming from the map, the standard, the natural partition, you can define a one-sided shift space, which is the beta shift, which has the same properties than the beta transformation. Now, the one-sided shift space, we can make a two-sided shift space by just taking the one-sided language and define correspondingly a two-sided shift space. And this two-sided shift space is a coded shift, and MMEs on the one-sided beta shift and the MMEs on the two-sided beta shift have the same properties and can be identified with each other. So in other words, we can apply in this case our main theorem about the uniqueness of the MME, and we can compute the MME. So for beta shifts, the MME is computable by what's the input here, by having an oracle approximation of beta and the knowledge that actually we deal with a beta shift. In the beta shift case, the quantity B of G on the other on the previous slide is just equal to 0, because there's for every length is a it's not 0, but it's very small, and you can compute how small it is. Next class are so-called S-gap shifts. S-gap shifts are given by a subset S of the natural numbers, and then you define the S-gap shift on the shift of the symbols 0 and 1, where you take a block of zeros and add a 1. 1 is the spacing element in that case, and the block can be as long as the length of the block belongs to the set S. So in other words, the generators would be just 0 to the power S1, where little s is in S. And again, in this case, one can compute the Vere-Jones parameter, one can compute the unique MME. There are generalizations of S-gap shifts to multiple gap shifts, which are just the same, now allowing more symbols, and they are precisely the same. You can compute the MME. Let's look about a shift space where we do not have a unique MME. One example is classically, the first example was the so-called Dyck shift. Dyck shift is a shift space on 4 symbols given by brackets and parentheses. So you have a pair of brackets and a pair of parentheses, and the Dyck shift is the shift space of all sequences where the parentheses and the brackets open and close in the right order. In this case, for the Dyck shift, there are 2 ergodic MMEs, precisely 2 ergodic MMEs, and our result also can be applied to prove that these ergodic MMEs can be computed. So these are the positive results. So all these standard examples, we immediately get the computability of the MME, even when it's not unique. But it turns out, in general, some really bad things can happen. For example, we have in this first theorem, we have an example of a coded shift such that if we take the first capital N generators and the first M elements in the language, we can always change the coded shift, adding different generators, adding different words in the language, such that the concatenation sets have larger entropy than the residual sets. The language of the initial segments and the generators of the initial segments are the same, but the Vere-Jones parameters differ by 1/2. So in other words, in this example, independently how long the input of generators is, how long the input of the language is, you always can change later on the coded shift for larger generators, for larger words, such that you get a different Vere-Jones parameter, which is uniformly bounded away from the original Vere-Jones parameter. Particularly the Vere-Jones parameter is in general not computable based on access to the generating set and the language. One needs some additional information. So alone with the generating set and the language, you cannot compute the MME, at least not in general. Now, in all those results, so far, we have not considered the case where the residual set has a larger entropy than the concatenation set. But I briefly mentioned that in this case, the MME is not unique anyway. But let's look at this case where the residual entropy is larger than the concatenation entropy. And let's assume we are in a situation where the MME is unique. And there's an example where this happens. And even the Vere-Jones parameter is computable, but the unique MME is not computable. So in other words, there's a very, very fine line between the space of coded shifts where you can compute the unique MME and the space of coded shifts where you cannot compute the unique MME. And of course, then there are all these coded shifts where the MME is not unique at all. And that is the end of my talk. Thank you very much.
Any question to the speaker?
No question?
No question. If not, let us thank the speaker again.
Thank you.
So our next week, the talk will be given by Professor Falconer. So I'll see you again there. Bye, everybody.
Bye.